right, welcome everyone to Seabird University. This is our fourth and final session for 2024. So thank you for joining. Just some quick housekeeping. There will be Q&A during the presentation, at the end of the presentation, and you can enter all of your questions through the Q&A box there at the bottom of your toolbar. If you have any issues with sound or audio or video or anything, you can also type your questions in there and I can work with you to try and get that sorted, but hopefully there will be no issues. With that, I will pass it on to Connor and Ben to get started.
Good morning. My name is Ben Crossen. I've been with Seabird since 2019, so about 5 years. Excited to have everybody here. Go ahead, Connor.
Yeah, and I'm Connor Bacon. I've also been with Seabird for about 5 years, and we're both members of the support team and are very excited to have everybody here.
All right, so we'll just jump right in. So today we're looking at advanced data processing for CTDs, dynamic corrections for CTDs. So let's get rolling. Okay, so the section of this course describes using Seabird data processing software to make dynamic corrections when profiling. So when we finish this module, we should be able to align connectivity and temperature data relative to pressure and filter your connectivity data so it matches the time response of your temperature data in an SBE 19+, and as well as the 9s and 25s. So and also removing effects of the connectivity cell thermal mass from your data. So the most typically used modules here, they're described in the processing manual or Seabird data processing manual. You can also find some helpful information via the help section of the software, which you can see in this slide here. There's a little option for that as well. And that's included in our Fathom software as well.
All right, so these are the names of the processing modules in Seabird data processing. They're all listed in the order the way you normally use them. The process starts with data file conversion, then progresses to data filtering and alignment, then additional post-processing depending on the situation. So in order, you'll have data conversion, filter, align CTD, cell thermal mass, loop edit, wild edit, filter, derive, and bin average. The following packages or modules then operate with that converted data. All right, next slide. So the thermodynamic equation of seawater 2010, that first line is the equation which is used in all modern calculations. The advanced modules, which are listed here, are optional, but can address specific needs for your research project without needing to learn how to use multiple pieces of software. Our command line option also allows for easy script execution and automation. The modules listed on this slide are all meant for modifying your file and extracting data. The ASCII in and out modules are a straightforward way to convert your data for use with Seabird software or the third-party ASCII compatible software. Section, split, and strip allow you to extract data in different ways that can save you time from having to manually do so without needing to convert the file to another type or export to a third-party software like Excel. With these advanced processing modules, your research can achieve even more accurate results and integrate cleanly with a wide range of applications. I think you're muted, Ben.
Apologies there. Am I good?
Yep, you're back now.
Okay, sorry. We're on. Apologies. Yes. So by reprocessing, we specifically mean don't go back and run your process data through multiple times. Start from the raw data file and the associated calibration information and start from scratch. So each module will generate a separate file for each step, which allows you to go back and redo things as many times as you need in case you need to experiment with the range or the variables in your data set. So averaging samples will have a dramatic effect if done too early, which could lower accuracy and hide nuance in your data. So what we do is we select our newest cal file that is essential with getting accurate data conversion. Most CTs will use an XML.con or a .con file provided after service or within order. And the data is either saved in memory, offloaded in real time, or both, depending on the system. We're using these files to generate a converted file or a .cnv, essentially a space delineated converted data file with the header. And this is the first essential step for data processing.
So once you've selected the files you want to process, the next step is to choose the variables you would like the software to convert. You can do so by selecting the Select Output Variables button on the second tab, Data Setup. This tab also has many other important output configuration settings, such as whether you only want to output upcast or downcast data, whether or not to use water sampler bottle data, your output format, and even the range of scans you want to process in your hex file. If you aren't sure what to choose, the defaults are generally applicable. Next slide, please. So this slide actually shows what the output variable selection screen looks like. When you have a valid XML.con selected, the software will automatically generate a list of valid variables that you can output. These variables also include different options for their units or different measurement standards, such as temperatures ITS 90 and its older counterpart IPTS 68. Be sure to double check your selections, as these cannot be modified in any later step. The derive step does allow you to add more variables that aren't listed in this step, but you cannot go back and, for instance, change your oxygen saturation from percent to milligrams per liter. So there we go. Perfect. Next slide, please. Because the flow rate determines the time constant for the Seabird connectivity cell, different systems respond differently. So filtering is the step that we recommend for adjusting your data in that to offset this error. Different processing steps are required for different CTDs due to the differences in their processing. The filter function is a valuable tool for removing outliers from your CTD and T and C data. When the 9 Plus is running, it has a built-in system for matching the tau of T and C. And other systems like the 25 Plus may need filtering to achieve maximum data accuracy. We generally recommend that for the 19 Plus, the first step after converting your data should be the filtering step.
Okay, so we have a little bit of example here. So this is a bit or digitized noise that could be seen if you do enlarge your plots enough. So in measuring the low pressure signal, there is a digitization error that may be removed by filtering the signal with a low pass filter. This has an effect of improving the resolution of the pressure signal by smoothing the digitization jitter. And so for the 9 Plus, you may only use this when using a fine scale or loop editing. For others, this is to match the sensor response. So the left plot on the screen shows some dithering in the data that is eliminated by filtering the pressure. So SB data processing software has nominal time constants, and the manual also has a list of nominal time constants for each CTD package. Filtering is done for two reasons: to match the time constants of the temperature and connectivity sensors, and also to smooth the pressure signal to minimize digitization noise, and preparation for removing loops in the data with loop edit. When smoothing pressure, use a filter that is approximately 4 times the sample rate. And we have some examples here. I'll just point out the 19 Plus sampling at 4 Hertz. That's 4 times a second, so about 1 second or so.
So alignment is a crucial step in addressing a common source of salinity data spiking, the time difference between sensor readings. If not properly aligned, that will cause spikes. Alignment is literally the distance between sensors and the combined effect of that time difference and how it causes poor data. Our CTD systems are plumbed based on the sensors ordered with the unit, so may have slight differences in alignment between individual CTDs. While we do follow certain rules to ensure you're getting good data, you may need to use the align function to reduce spikes in your data. Next slide, please. So here's an artificial data set with a step change in temperature and conductivity. Temperature is the blue trace, conductivity is the green, salinity is the red. And the top plot, the T and C are perfectly matched, yielding a plot of salinity that is as expected. In the bottom left plot, conductivity lags by about 0.08 dbar. And you can see that a negative spike shows up in the salinity data. In the bottom right plot, conductivity leads temperature by about the same degree, leading to a positive spike in salinity. This is a simplified plot to make the differences more pronounced. This behavior can be present in any CTD system built by any manufacturer. It is caused by a mismatch of the T and C measurements in relation to pressure. This is not a sensor artifact. Any T and C pair using any technology will produce an error in salinity if a scan contains measurements from different water parcels. A note about the direction of the salinity spike. The direction of the salinity spike is also dependent on whether T and C are increasing or decreasing with increasing pressure. In the examples above, if T and C were decreasing rather than increasing, the salinity spike would be going in the opposite direction. Keep that in mind for our future examples here. So yeah, so you can see here, for our 9+, this alignment is done automatically as part of the data collection process. There's also some dependency of what you plumbed into the system. So the cause of this mismatch is mainly the slow response time. You can observe the displacement here between the up and the down casts. Aligning these two would help close that gap for a bit of a cleaner looking data set. So because the 911 system is well characterized, an alignment of the data stream is done automatically in the 11+ before the data is transmitted to your computer. With the TC duct in one place, an alignment of about 1.75 data scans, or a little under 0.07 seconds, is done in incoming data. A linear interpolation between scans is done to implement the alignment of non-integer number of scans. Misalignment that differs from the nominal values can arise from plumbing changes, which can influence pumping speed. A slower pumping speed increases a water parcel's residence time in the TC plumbing, and will require a larger shift in the data scans. A faster pumping speed will decrease the residence time in the TC plumbing and require a smaller alignment value. Note that the advanced values are given in seconds and are relative to the pressure channel. So our software and manuals provide recommended settings for defaults to use when processing your CTD data. These settings have been experimentally determined in the past and are reliable in most applications. Changing them will influence your data, but you're free to do so if you believe that it will improve your data quality. We'll explore some of the different ways that you can improve data quality using these following modules. Slide. The align module itself is found as part of CBER data processing, and combined with cplot, our data visualization module, can be used to examine your data and determine the best settings for your system. We'll look at some examples in the next few slides. So here are some great examples of alignment and how adjusting the values in your software can impact your final data. So looking at our original data, for those of you using a small screen, it may not be super pronounced, but in the recording, you can take a look and see some of the minutiae here, but the salinity is showing quite a bit of spiking, as is the density you describe this generally as noisy data. Looking at the advanced 1 scan, 0.042 seconds, you can see the degree of the spiking is dramatically reduced. It looks a lot smoother and likely reflects the actual in situ situation a lot better. When you advance 2 scans, some of that spiking comes back. It's less pronounced than the original data, but still it looks like you've overshot a bit. Going even further, by advancing 3 scans, you're going all the way back around, and now the spikes are going in the other direction with about the same magnitude. So this is to really show that advancement can affect your data, and aligning with your pressure sensor and making sure that that time constant is all dealt with can really, really improve and reduce noise in any of your data sets. So essentially it's raw, good, bad, and very bad. So you want to make sure that you're paying attention to the amount that you're advancing your data if you notice spikes. So by trying these different values, you can determine the best alignment for your system. You can control for plumbing and pump speed on most CTDs. Not all of them have the same perfect alignment settings. So while the default values provide good data, trying multiple alignment settings may reduce noise. And the next slide, thank you. So this slide provides a similar example, but for the 19 plus. So when you see the spikes get larger as you move conductivity against temperature and radiate away from the center line, blue, that's the most accurate line. You can see it has the least amount of spiking. The intent behind this example is to demonstrate how to tell which way your alignment should be adjusted. So taking the raw data, you can see the middlemost value is the least noisy and the spiking radiates away from it, clearly showing your direction and magnitude from the offset and the perfect alignment. Looking for similar patterns in your data can inform you of the direction in which you need to modify your alignment values. Though keep in mind, the direction of your flow does matter. The earlier slides, like I demonstrated, show that. Thank you.
Okay, so some notes about conductivity cells and cell thermal mass. So we've got glass conductivity cell that stores heat. So a warm cell warms water moving through it. So we'll read a warm of correct. When we say warm of correct, what we're speaking about, correct is actually the true value, and that would be high. So we'll read warm of correct high. A cold cell cools water moving through it. So we'll read cold of correct or cold of true, which would be low. Water in the cell is warming or cooling to a different temperature than what the temperature probe measured before. So the conductivity measurement has temperature dependence. The conductivity cell itself is constructed of glass and plastic, and as such has a thermal mass, right? So when the cell goes from warm water into cold, the water that passes through the cell slightly warmed as it transits the cell, resulting in conductivity measurement that is high of correct, like we said. And conversely, the same thing happens when the cell comes up from cold water into warmer water. The water that passes through the cell is cooled slightly, resulting in the conductivity measurement that is low correct. So the heat transfer can be modeled and corrected. And here's a little bit of an example of that. So the data shown in this plot has already been aligned using aligned CTD. So reducing salinity spikes associated with the misalignment. We see what appears to be salinity hysteresis, but there is no temperature hysteresis. The feature that looks like salinity hysteresis is actually caused by the effect of cell thermal mass. Another way to check for cell thermal mass error is to create a temperature versus salinity plot and look at that feature in that plot as an open curve. So looking at this example, the upcast and downcast don't line up very well, especially towards the bottom of the downcast and the start of the upcast. And this is an example of what cell thermal mass may look like in your data. There are some default values that are in our CBER data processing software. There is a correction to the error that consists of an amplitude of a correction and a time constant of that correction. So it uses the difference between adjacent conductivity scans to calculate a new value based on the samples before it and and the two correction parameters. So this can be done for primary and secondary sensors in a 9+. CBER data processing has a self-thermal mass module that can make this correction and with an equation, which is a function of amplitude alpha, which you see here, and the time constant beta. Like many of the sensor-related phenomena we have considered, the heat transfer within the cell has a time constant. So where C equals the uncorrected conductivity and dT equals the temperature of the previous temperature. Okay. Thanks for joining CBER University. Thanks, everyone. Time to start the Q&A.
Yep. So we went over a bunch of different modules here. I'd love to talk about any of them or look at some more specific examples. Are there any in chat currently? All right, I see one here. How to determine the alpha and beta parameters for the 37 SMP. So that's a great question. So let's look into that real quick. Actually, we got one about the slides here that I might address quicker. Ben, could you pull up the first graph we showed for the comparisons? I believe it was the filtering one that they're suggesting. So I think that would be slide 15. Perhaps. I think it was this one. Okay. So yeah, we couldn't discern the differences in the lines. Could put out what we should be seeing. So yeah, this is where potentially viewing on a small screen can be a little bit difficult. But if you're looking at the blue line and the green line, the salinity line, the density line, you've got a lot of this a lot of horizontal spiking, right, in the signal. So on the salinity in the green line, I think it's the most pronounced. You can see a lot of noise as the data comes in. But with an alignment, you can see that the magnitude of that spiking is reduced, and it looks a lot more like a solid line. Like
I think we're
a
looking at the wrong one, Connor.
Are we?
Yeah.
Oh, wrong graph, 2 plots. Okay, let's see. Oh, this one. Yeah.
Is it the
that
T
I
and
think is it.
the T and C alignment?
Wrong graph. They say it was 2 plots, so I think it's the next one after this.
It has 2. Okay.
Yeah, next slide. I think
is it
this
this?
one. It was before this. Let me pull up my copy of this PowerPoint and let's take a look.
Is it
maybe
this one?
The filtering pressure, I believe. Slide 13. There we go. Found it. So, okay, Ben, can you speak to this one?
Yeah, so I think this is an example from a 9+. So this was with a fine scale and loop edit, I believe. If I remember correctly, there's a couple places that it's not as clear as I would hoped it would be, but was there a question between the two?
Yeah, the
Or
question
go
I
back
think
and
is
see.
what should they be looking for specifically? And I think I agree, it's somewhat difficult to see,
Yeah.
but from our end, and when you get this recording, you should be able to see this a lot
Yes,
more clearly.
yes. So filtering, so it's pressure filtered with a 0.15 second time constant. So maybe we have it in this. I have it in this slide beforehand. I don't have that. So
Yeah, so essentially what you're looking at here is the amount of jitter in the signal has been dropped. We're getting a lot more smooth lines in the salinity plot. It's reducing noise, improving that signal data. But I agree. This is a good slide for demonstrating the effect of this conversion, but perhaps while streaming, it's a bit difficult to read.
So a note about this one as well. The left plot being the raw data. There's some spots in there which you can see like with filtering and the loop editor wild edit. There's a bit of what looks like heave at certain points. If you're paying attention to somewhere around a sort of the middle there, where the cross section of both plot lines meet. About the second half of that on the left-hand side on the raw data, you can see quite a bit of what looks like heave. Like you see this, it almost looks like the signal is flat or going upwards when they're actually on the downcast. And when we start to filter that stuff out, it basically eliminates those points, or at least connects the points a bit easier. So there's a couple gaps. It's, again, hard to see on this specific plot, but there's a couple gaps on the right-hand side after we've filtered the data where you don't actually see that. It's hard to point out, but yeah, it looks like the whatever was done filtered and edited out those loops or the heave from the ship. So we don't have that upswing in the downcast. It's just a strict downcast.
Yeah, and the reason loop edit has the name it does is because a lot of the time when you're looking at severe ship heave, you will observe on a depth plot actual loops forming in your data as your system goes back up and then back down again. And the way that the software works is it's looking for a change in the direction of your movement that exceeds a certain value to trigger the upcast. And by having your system filter out certain amounts of directional changes, essentially caused by your ship heave, it allows you to remove doubled up data or data that's not really the highest accuracy because it's going back through water. It's already sampled, already eddied. And that's the idea behind loop edit. Wild edit is also just an extension of that.
And I believe you could set the value too. Like if it's if while you're going through the downcast, you can, I believe, put a value in there if it starts to go up by a certain amount of pressure, right? The filtered pressure, like we were talking about. That's kind of what the right plot in this one is assuming that. So if we see a decrease in pressure over a certain amount of time, the software will completely filter that out. And that's usually what we see with what we call ship heave, or you get this loop that kind of goes up. You can get rid of that by filtering out that bad pressure outlier that's actually not part of the downcast. So.
Exactly. So as an example, so if you're for our beautiful Pacific coast and you're doing 1,000-meter cast, you're expecting to see waves of about 1 meter. You'd set your loop edit to filter out any changes less than 1 meter, less than or up to 1 meter. And then when it finishes the profile and starts the ascent, the system will expect you to exceed a single meter in pressure change, and we'll trigger the upcast at that point. But any changes smaller than that will be triggered for loop edit. So I see another question. Someone inserted an incorrect sampling rate, 24 instead of 1, in the configuration file of 9. Seems that their non-bin average values are better. I would agree. What are their other options to save the observations? I'm not quite sure how to answer that one, because part of the answer to that is if you've already bin averaged the data and you don't have a copy of the non-bin average data, I don't believe there's much you can do on that. But if the question is whether we recommend to not bin average your data as a first step, I think absolutely. Yeah, Ben, perhaps do you have another answer for this one?
Um,
We'd
I
be
think
happy to answer it in
sampling
more
rate
detail if
and
there's a different answer you're looking for here.
non-bin average. I would assume a lower sample rate, and yeah, not using non-bin average would, for averaging, um, you might have the same or very close measurements back to back to back, so it might not look as dynamic, I guess. Maybe that's what they're getting at. I'm not entirely sure. Um,
Yeah, if they mean by saving them, as in getting this data set back to how we'd expect it to look with a properly set up
mhm,
9.
mhm.
Yeah, I don't believe there's an advanced module that would allow you to interpolate that data that's already been averaged, unfortunately. Which is just a limitation of
Okay.
how the files are saved, how that is saved. So
Gotcha.
like we said, at each step of the processing for each module, it'll generate its own file, and you can append your own suffix to it to keep track. But long the short of it is, when we do data processing, we'll generate the CNV for filter. It'll generate a second CNV with the filtered options. For a line, it'll do a third that has the filter and aligned options. And if you
Mhm.
say don't want to use the alignment settings that you already used and have your third CNV, you can take your second CNV, use that with align again with different settings, and generate a new CNV for your align module that you can experiment with.
Yeah, looks like Chris also answered some of the questions in chat too for that. So,
Excellent. Thank you. I may need to take the alpha and beta parameters offline for the 37 SMP. Some of these questions we'd be happy to answer, though for the sake of time, we may answer them as part of a tech support request. So let's see, how do you elaborate in the wild edit module?
I think we sort of touched on this about some of the Ship Heave stuff, but I'll let you go, Connor.
Yeah, so I'm just going to really quick. So the wild edit is looking at standard deviations as opposed to pressure when you're trying to adjust it. You're looking for different scans of data and looking at the variability between each one. So you can set a range of how many standard deviations away from a mean that you want to remove. It's essentially a stronger version of wild edit and filter, but has its own specific use case. Like we say with some of these, they're a little bit more, some are more used, some are less used. I'd say wild edit does tend to be one of the modules we see used less often. But for people whose research requires them to use standard deviations or have their own process for determining the amount of outliers they'd like to remove, this can be an extremely powerful tool. And it'll mark scans as bad, and you can choose to exclude them or not. That's also a very valuable step with wild edit.
Loop edit as well. Same thing.
So as far as steps go, really it's a single module. So you're entering in your file, you're choosing the number of standard deviations that you want to remove. You choose the scans, the scan range, how many scans you want per chunk of your data that you want the standard deviations to be looked at. And then from there, it will process the data for you.
I think for the alpha and beta parameters for this 37 SMP, it might be something we can talk about a bit further. You can always reach out to us at our tech support email, techsupport@seabird.com, and we'll get a case started with you and have a discussion.
There don't seem to be any values in the tables for the 37 in the manual, for instance. So that might be why there's
I see.
the question. Only really covers the 25s and 49s and 9s and stuff.
I see. Yeah, the majority of the presentation was more geared towards profiling CTDs rather than moored CTDs. So the 37 wasn't necessarily part of this, although some of the steps processing data wise are similar. But obviously, you're not going to have your loop edit and your while edit because you're not profiling through a water column. So
I will say I have seen some customers use their 37s for profiling applications, just hand over hand rope mounted applications.
mhm,
And in those situations, we call out a line and loop edit definitely as important steps
I see.
for post processing. But yeah, like Ben said, this is mainly focused on profiling CTDs, though it is widely applicable for sure. And I believe we answered the wild edit module one already. So if there are any other questions, let us know in chat. Otherwise, we may adjourn the meeting here at around 8:40.
Looks like that might be all of the questions. So thank you, Connor and Ben and Dave, for joining there to answer all the questions. That was a great presentation. And for everyone attending, this presentation was recorded and will be posted up on our YouTube channel. And I would expect that to be there within a week or so. So if you want to revisit anything, you'll be able to do that. And as I mentioned, if you have any other questions, you can reach out to tech support. And they'll get a case started and work on that for you. But if there's no other questions, I think we can end it. And everyone, have a good day, everyone. Thanks for joining.
Thanks.
Thank you, everybody.
Take care.